All right, let's begin. Welcome to today's exam. So we're just going to do some extra stuff, CS3510, extra, I'll call this tree DP. So today's the exam, dynamic programming and NP completeness. So I'm going to record one quick-ish, very short video on an extra thing in DP and then an extra thing in NP completeness. First thing I want to mention with dynamic programming is one perspective is that it is a time-space trade-off. In the sense that you recall in, like, for example, a Fibonacci recursion tree, you have a recursive call repeated multiple times. Forget it, just write that answer down and then use that to build up subproblems. That's kind of one perspective of dynamic programming, is that like you can reduce time complexity by increasing space complexity, and since no one really cares about space, the algorithm speeds up. What I want to mention is, first off, it's not really a trade-off, because you can trade the time for space, and then after you're finished, you can get the space back completely for free. So I'm going to implement to you a dynamic programming version of Fibonacci that is the dynamic programming version of Fibonacci, but it doesn't use an array of size n, right? So fib of n, if n equals 0 or 1, we can return n, and we're computing the nth Fibonacci number. Let's, here's what we would used to do. We would say dp of 0 to n would be the array that we allocate normally. I'm not going to do that. Instead, what I'm going to do is just say dp of 0 to 3. No, to 2. So dp0, dp1, and dp2. I claim we can get away with computing the Fibonacci numbers without storing all n numbers. We just really need the last two numbers. Because if you think about it, this Fibonacci number is the sum of this one, and this one is the sum of this one and this one, right? So at any step, you only need to look at the last two. It's a very local thing. Some DP problems require perhaps the whole array. Not this one. It's only a constant of the past, right? So what we would do at this step is we would say for, we have to do our base cases. dp of 0 is 0. dp of 1 is 1. And then we would say for I in 2 to n, we would say dp of I takes on dp of I minus 1 plus dp of I minus 2. Okay? But we don't have dp of n. We have only 3 variables. So what are we going to do is we're going to juggle the variables in such a way that we keep swapping them around, so that the last variable used is going to be the new one that is in. We need this variable to be the sum of the 2 previous variables. So what we're going to have to do is the oldest variable used, we're just going to overwrite it with the new content of the other 2. So we have 3 variables that we're basically juggling around. The math will define this as, and we'll say I mod 3, which is dp of I minus 1 mod 3 plus dp of I minus 2 mod 3. For example, give me a number like less than 10. 7. Okay, everyone says 7. Normally, we would say dp of 7 takes on dp of 6 plus dp of 5. But here, what's 7 mod 5? So we would say dp of 2 takes on dp of 1 plus dp of 0. Which is definitely the case also when you're computing dp of 2, right? Wait.
You said mod 5.
Sorry. Oh, mod 3. Was it 7 mod 3? What's 0 mod 3? Sorry, what's 6 mod 3? 5 mod 3? 2. Yeah. Now if you were to compute dp of 8, it would do the same thing, right? Let me just write it out. dp of 8 should be dp of 7 plus dp of 6, right? What is 8 mod 3? What is dp of 7? Yeah. So notice that, for example, forget these lines and look at these lines, okay? This is what's computed. The next line is going to be this one. 2 contains the oldest one. We're going to now overwrite 2 with the sum of the other ones. We repeatedly do this, we're just going to get the Fibonacci numbers, right? But now instead of n variables, we've done it with 3. Why don't we do this? Oh, by the way, what do we return? This is not an easy question. Return dp of what? Yeah, that's going to contain the answer that we want. Why don't we do this? Why don't we write code like this? It's ugly. It's annoying. We have to do some math. Why does that work? I'm not even convinced. I have to write it out a little bit and explain it. You can perform dp. Think of it as a time-space trade-off. Fine. Then do something else to get the space back. But we don't ever care about space, so writing it out like this is just really annoying. The moral here is that you can trade time for space, but then you can always get the space back. So don't think of it too much like a time-space trade-off. But also, don't bother writing dynamic programming like this because it's really annoying. For example, let's suppose we sped up Fibonacci from n array elements to 3. Okay? Let's suppose we were trying to do the same thing for longest sequence problems. Okay? Let's say longest common subsequence. We have an n by n array which takes n squared elements. We don't really need all n squared elements because in some sense one cell is only looking at 2 cells from the past, right? Kind of. What is the maximum amount? If we did a very complicated, here we can do mod 3 and get away with it. We could do a more complex organizational strategy here. How could we save space? Suppose I didn't want to actually store n squared cells. But then you have to store which cells reference each other. Similarly here, as this only references the past 2, certain cells only reference some other past 2s.
Different cells reference different past 2s.
Exactly. But that's true here too. dp of 6 is dp of 5 plus 4. What you could do, and I'm trying to explain this as kind of like why you shouldn't do this. You could do this cell, okay? Then you could do these 3 cells. Well, no, forget that cell. You could do those 2 cells, right? Then you could do these cells, and then these cells, and then these cells, and then these cells, right? Each time you do a cell, let's say you only keep 2 stripes at any moment, just for simplicity. Technically, you could get away with 1 by overwriting, but suppose you could just get away with 2. You erase the 3rd one and add a new one. So this structure is increasing in length. The longest it'll ever be is the length of this diagonal, which is how big? Yeah, it's like 2n, O of n. So that, you can technically solve longest sequences in O of n. N of O of n space, thank you, yeah. Why don't we do it? I don't want to figure out the math for that. What is the index of the elements in this diagonal? The table is never written down, it's fully virtual, and then the array elements, somehow a of I would have to be a function of 2 other indices. The math for the diagonal can be done, because it's not the chain matrix diagonal either. It's a different one. The math for the diagonal can be done, but it's just, why? It's just an example that you can improve space. Don't worry about space. Space complexity, it's not the job of the algorithm designers, it's more of the job of the engineers. So we won't do this, but someone else could. Let them figure it out. That's the answer. Questions on that? Okay, let's talk quickly about something called tree DP. Before we do that, does anyone remember the house robber problem?
Oh, yeah.
Right. You have an array of elements, right? And you have an array of houses with value. Okay? And you want to choose some set of houses to rob, but you cannot choose 2 houses that are adjacent, otherwise they'll set off an alarm. This is just a quick review. So you want to choose some set of houses that are non-adjacent that maximizes the amount you can rob. What is that answer here?
It's 9 and 9, right?
Yeah, I think so. That sounds right. Can't choose anything else. What was the recurrence? Do you remember?
You either rob or don't rob the current house.
Yeah. You consider, exactly. No, that's very important. So you consider dp of I in English is assigned to be the max you can steal only considering houses 1 through I. So the recurrence works in such a way that the next house, you consider prefixes, and the next house can be made as a local decision of previous things. So you either rob or don't rob, and you take the max of those two, right? Everything in this world either is or isn't, okay? If you rob the house, you would earn what? House I plus what? I minus 2. Because you could not rob house I minus 1. But it's the max you could steal if you considered this house, if you robbed this house, considering these houses. So whatever that is going to be written down there for us, right? And then if you don't rob the house, what goes here? Correct. Yeah. Each time, each thing stores an answer for you, right? So this was just a quick review on house robber. Suppose you're not given the houses in a linear fashion. Suppose you're in a subdivision. And what is the best way to represent adjacency in a subdivision if not a binary tree? Suppose you're given a binary tree, perhaps full, incomplete, perhaps not. Okay? This is, let me do better, okay. Okay, something like this. Let it not be totally full and complete. Let each house be assigned to it a value. And you want to steal the maximum you can from all the houses, except you cannot pick two that are adjacent, in the sense that one is the parent of the other. So for example, if I were to ask you about these two specific binary trees,
So you can't steal the parent and then steal the child.
yes. But you can steal a parent, you can steal a child and its grandparent.
Yeah.
So what is the max you could steal if you were given a tree like this? Where's 6? You can't steal these two? Is that the max?
Yeah, isn't that?
This one?
Yeah.
This one?
Yeah.
Is that the max?
Oh, yeah. Oh, wait, you can also steal 1. Yeah.
Yeah. Can you steal anything more?
No.
Yeah, I don't think so. Okay, what about this one?
Is that a 19?
Where?
Is that a 19?
No, this is a 9, sorry. Just smudging everything up. Where? Okay, so it appears we could DP. We'll make a problem as a function of a smaller subproblem. What should the size of our array be? It's a trick question. There is no array. That's the trick question. The lecture is titled Tree DP. So what we're going to do is, the moral is we're not going to say, oh, let DP of, let's do 0 to n, 0 to n. No, we're not going to do that. What we're going to do here is instead of an array, we're going to do DP on a tree, where our data structure that holds the smaller answers for us is literally a tree. Now, tree DP, it's interesting to note that practice has advanced far more than theory. Theorists, I don't think they really care about tree DP. Competitive programmers appear to, and it's a technique that, like, if your problem is too simple, sometimes you can get away with an array instead of actually doing tree DP. If your problem is too complex, you might require tree DP. So teaching it, it's like this is the simplest example I could find that requires tree DP, but it's not simpler. That could be done with, that it doesn't appear to, I don't know how to do this without tree DP is what I'm saying. So, like we call an English sentence each element of an array, and we define it as a subproblem. If I were to ask you for any, first off, what shape should our data, what kind of tree should our data structure tree be? Yeah, but what kind? And more specific. I'll tell you. Basically, let DP be a binary tree exactly like that in the input. Okay? What this really means is we're not going to even necessarily have a different data structure that we do tree DP on. Instead, we're just going to write over the same tree. In English, what should DP of, let's say, a vertex V be? We're going to we're going to write over the tree with smaller answers. What ought to this be? And this is not like an I. Let's say we have a vertice of a tree. As a subproblem, remember in the house robbers problem, we said DP of I in English is the maximum you can earn if considering houses 1 through I. What should DP of V be then in English? Yes?
That'd be like the rest of the tree without the vertices and the children of the vertice we're talking about. So
Be a little more specific.
I'm just like, like the tree. I'm not sure how else to describe it.
If V was 9, what would be considered?
It would be 3, right?
This one?
3 and 5, yes.
I'll go the other way. At least I think I go the other way.
2, 3, 1.
9, 2, 3 is what I'm going to consider. I'm going to say this is the max can steal, considering, yeah, V and all its descendants.
Does that mean you have to go backwards up the tree then?
Sure.
Like starting
But then recall in DP, sometimes the last thing that you write down is the answer that you want to return. Correct. So you want to return the root, because that's the max you can steal considering the root and all its descendants, which is the entire binary tree, right? The base cases are a little unwieldy. If V is a leaf, DP of V should be what? And this is not a 0, this is a circle.
value of D.
Yeah, I don't have my notation good. What should we call that?
V dot val.
V dot value, okay. Okay. If V has 2 descendants, so for example, like that, what should DP of V be? Not quite.
The max of the 2 descendants, or just the value of V.
I'm going to say val because I'm lazy, okay? Or what?
Or the value of the 2 descendants.
We'll say v dot l dot val plus v dot r dot val. Forgive my notation, this is horrible. But we understand what that means, right? V dot l, let's call this v dot l, and let's call this v dot r. Okay, hopefully that works, right? Okay, what if there's only one child? Yeah, same with this, okay? What if, okay, we've done the base cases basically. What about the general case? Let's suppose V is here. Let this be V dot L, let this be V dot R, let this be V dot L.L, V.L.R, V.R.L, and I'm going to write this bigger. V.L.L, V.L.R, V.R.L, V.R.R. Okay. So we want to know the max you can steal considering V and any of its descendants, right? And suppose that we've already computed smaller subproblems for this one, this one, this one, this one, this one. These are all small subproblems. We've looped over the tree, leaf to root, and we're increasing the knowledge about things. What should the first consideration be in our recurrence?
Whether or not to steal the current node.
Perfect. What we want, and this is important, you have options. DP is brainless in the sense that you just take a function of those options. You want to maximize something, so you take the max of choose, I'll say, robbing house V or don't. Those are your two options, okay? If you choose to rob house V, you cannot take VL and VR, that's correct. But what can you take?
L.L, V.L.R.
You can or can't?
You can't.
You can. But what if you don't? What if it's not valuable? What if it's not appropriate value to take V.L.L? Like choosing that one prevents you from choosing one of its descendants. Let's say this is 1,000. 10,000, okay?
You can't take any of its descendants?
No. You just, you can choose V, and you can choose this, and this, and this, and this.
Yeah.
But by choosing to steal this one, you prevent it from choosing to steal that one.
Yeah.
So maybe you don't want to steal this one. Answer?
Should have already calculated what the best for V.O.L's descendants are.
Correct. You won't steal V.L.L, but you'll calculate this as, instead of adding V.L.L, you add dp of V.L.L. That's going to give you the max you can steal of considering V.L.L and any of its descendants, which recursively is going to be the problem. So if you choose to rob V, this is going to be V.Val plus dp, say it for me?
V.L.L plus dp of V.R plus V.R.L. V.R.R.
Okay, let's double check, is that right? So just to be clear, it's choosing this one and potentially choosing whatever these are going to be. Okay. Now if you don't choose to steal,
V.L plus V.R.
sorry, let me draw it. If you do not choose to steal this one, which two nodes are in consideration?
Children.
DP, V.L, DV of V.R.
Okay. I guess we could talk about the runtime. Suppose there are n nodes. How long does this take? If you have n nodes, let's say you have depth at most log n. Let's say it's a nice binary tree. Make things simple. I'm not looking for a serious discussion, just kind of a high level thing. Yeah.
I mean, intuition tells me at least O of n because you have to go through at least every node once.
But does the time take less than O of n? Sorry, not less than O of n, but does the algorithm take O of n? Can you do it, or is it n squared or something? Yeah, you calculate that one. Let's say these are leaves. Calculate that one, that one, that one, that one. Calculate that one. It's the max of a sum of things. There's just sums of finitely many calls to the past. In fact, so you could technically figure out a way to I wouldn't try, but memoize it. Not memo. I'm using that word wrong. Like constantify it with constant space. But don't. But okay, so that works. Questions? I can't. So when would you want to use TreeDP? I googled it. Like basically every problem that uses TreeDP takes as input a tree. So that's a pretty good indicator. I don't have any other intuition to share with you on when you would choose TreeDP over anything else. But it is an interesting technique. Yeah. You don't need an array. Sometimes you can use other obscure structures. Questions? Okay.